When you filter out highly toxic, carcinogenic water pollution, where does it actually go?
Yeah, that's the big question, isn't it?
Right. We like to think that when water runs through a purification plant, the contaminants just, vanish. But the terrifying truth of traditional water filtration is that it doesn't destroy toxins, it just traps them.
Exactly. You're just moving the problem.
Right. We are essentially pulling invisible poison out of our drinking water only to create these concentrated toxic landfills somewhere else. So what if we could stop moving the trash around?
I mean, that is the dream.
What if we could build a microscopic incinerator out of common plastic and rust that literally shreds these pollutants out of existence?
It is a fundamental shift in how we approach eco-friendly water decontamination. For decades, we've relied on physical separation methods, so sieves, membranes, activated carbon.
Yeah, standard stuff.
Right. But as industrial waste standards become increasingly stringent and water-stressed regions struggle with limited accessibility to complex infrastructure, those older methods are hitting a wall.
Yeah.
We desperately need systems that prevent secondary pollution entirely.
Okay, let's unpack this, because the solution we are looking at today is truly mind-blowing. We are doing a deep dive into a fascinating new study from the Journal of Materials Science.
It's a really incredible paper.
It really is. We're going to explore how a team of scientists managed to combine common iron rust and a very specific type of transparent plastic to create a reusable light-powered factory. And this factory mineralizes water pollutants down to harmless molecules. You might be surprised by what's hiding in your water, and even more surprised by what it takes to actually destroy it.
Yeah, the research focuses heavily on a class of contaminants that are notoriously difficult to eliminate.
So organic dyes.
Like from clothing factories. Exactly. In an industrial context, like textile manufacturing, these dyes are formidable, complex chemical pollutants. The scientists targeted two primary culprits to test their new material. The first is crystal violet.
And reading through the paper, crystal violet isn't just a tough stain to get out of fabric. It's a non-biodegradable caissonic dye. The researchers note it is heavily classified as a carcinogen, and more specifically, it's clastogenic.
Yeah, and that word is important. Clastogenic means it actively causes chromosome breakage in living cells.
Wow, so it literally breaks DNA.
It does. If it enters the aquatic ecosystem, it doesn't just poison the wildlife, It disrupts their fundamental genetic material, leading to severe mutations. And because it possesses a positive electrical charge, that's what makes it cationic. It readily binds to cell membranes and tissues.
So it just builds up in the body.
Right, accumulating as it moves up the food chain.
Then there is the second dye they tested, rose bengal, which is an anionic dye, meaning it carries a negative charge.
And rose bengal is just as stubborn regarding natural biodegradation. But its biological impact is uniquely alarming. The studies cited in the research show that rose bengal is highly toxic to the human corneal epithelium.
Wait, corneal, like in your eye?
Yes, it physically degrades the intercellular junctions in your eye tissue. So we are dealing with complex, highly resilient molecules that traditional filters simply condense into a concentrated sludge.
Which brings us back to that problem of secondary pollution. If you just filter out the crystal violet and the rose bengal, you still have to put that toxic chromosome-breaking sludge somewhere.
Exactly.
This is where advanced oxidation processes, or AOPs, enter the picture as the potential savior.
If we connect this to the bigger picture, AOPs represent the holy grail of zero-waste water treatment. Instead of physical separation, AOPs utilize chemical destruction.
So destruction, not filtration.
Right. They generate highly reactive free radicals in the water. These radicals relentlessly attack the organic pollutants, breaking their complex molecular bonds and converting them into stable, safe, inorganic compounds.
So it's not magic, even if it sounds like it. If traditional filters are like a sieve that catches the big pieces of trash but eventually gets clogged, AOPs are like a microscopic incinerator that actually burns the trash out of existence so there's nothing left to throw away.
That's a perfect analogy. The study mentions mineralization.
Mineralization. So we are talking about tearing these dye molecules down until there is literally nothing left but basic water and carbon dioxide.
You return the chemical components back to their most basic, harmless, natural states. Nothing is left to throw in a landfill. And to power this microscopic destruction, the researchers utilized a semiconductor photocatalyst. They chose a very specific phase of iron oxide called alpha Fe2O3.
We're talking about hematite, essentially just rust.
It is rust, yeah, but engineered at the nanoscale. Hematite is thermodynamically stable, it's non-toxic, and it's naturally abundant.
So it's cheap.
Incredibly cost-effective, especially compared to using rare earth metals for catalysts. But the real reason it is utilized in advanced oxidation processes is its specific optical properties. Hematite has a narrow band gap of about 2.1 to 2.3 electron volts.
Okay, for those of us who might be a little rusty on semiconductor physics, how does that band gap actually power this process?
Good pun. So for a semiconductor like hematite, you need just enough energy to kick an electron across a band gap from its resting state in the valence band up to a higher energy state in the conduction band. Hematite's gap is right in that 2.1 to 2.3 electron volt sweet spot.
Okay, I follow.
That means standard ultraviolet light is perfectly tuned to act as a catapult. When UV light hits the hematite, it catapults an electron across the gap, creating what we call an electron hole pair.
So the electron is now energized and jumping around, and it left behind a hole where it used to be.
Right. And both the jumping electron and the empty hole are incredibly reactive. They desperately want to interact with the water and oxygen around them. That chemical hunger is the engine that drives the entire oxidation process.
But the researchers didn't just scrape some standard rust off a pipe to get these specific optical properties. The study goes into immense detail about how they had to build these nanoparticles from scratch to get them perfect.
They did.
They used a sol gel synthesis method, starting with iron-3 nitrate and water.
The sol gel process allows for extreme control over the final structure. They dissolve the iron nitrate in water, but they also introduce glycine into the mix. Glycine acts as a complexing agent. It binds to the iron ions and keeps them evenly dispersed in the solution.
Why is that even spacing so important?
Because the next step is an autocombustion process. The glycine acts as the fuel. As the mixture is heated and dehydrated, it auto-ignites. Because the glycine kept the iron ions separated, the combustion creates uniform particles rather than a fused, clumped mess.
Got it. And then they took that resulting powder and baked it at 550 degrees Celsius for 2 hours. I'm assuming that specific temperature isn't arbitrary.
No, not at all. It is the exact thermal condition required to crystallize the powder into pure rhombohedral alpha Fe2O3 particles that are uniformly 60 nanometers in size. It is a beautifully precise chemical recipe. However, despite this flawless engineering, hematite carries a fatal flaw in its physics.
Right, and that flaw is something called a short-hole diffusion length. The paper mentions it's only about 2 to 4 nanometers.
Yeah, and what that means in practice is that after the UV light catapults the electron across the band gap, the electron almost immediately falls back down into the hole it left behind.
Oh man, so it just gives up.
Pretty much. The excited charge carriers recombine in a fraction of a second. They neutralize each other before they have a chance to migrate to the surface of the nanoparticle and react with the water.
Wait, if the energy recombination happens in just 2 to 4 nanometers, how do we actually capture that energy before it fizzles out? How do we track the lightning in the bottle for you and me to actually use? We've built this perfect microscopic engine, but it keeps stalling before it can do any work.
To trap the energy, you have to alter the local electrical environment of the nanoparticle. That is where the plastic comes in. The researchers introduced a polymer called PMMA, polymethyl methacrylate.
Why PMMA specifically? There are thousands of types of plastics out there.
PMMA is an insulating, highly transparent polymer. Transparency is non-negotiable here. It ensures minimal interference with the photon flux.
Because the light has to get in.
Exactly. The UV light has to pass right through the plastic to hit the iron oxide embedded inside. But PMA's real triumph is how it interacts with the hematite. By mixing those 60 nanometer iron oxide particles into a PMMA and chloroform solution and casting them into films, the polymer physically restricts that rapid electron hole recombination at the interface between the particle and the plastic.
So it keeps them apart.
It essentially separates the charges, yeah, giving them the vital time they need to trigger the oxidation reactions.
It's like a custom-built, transparent greenhouse. It lets all the necessary sunlight in to power the plants, the iron oxide, but it keeps those delicate plants firmly rooted in place so they don't wash away in the rain.
I like that. And keeping them rooted solves a massive operational nightmare in water treatment. If you compare PMMA to other support materials, like if you just dump loose free nanoparticles into a treatment tank, recovering them is an engineering disaster.
You'd never find them all.
You'd need massive, expensive industrial centrifuges to separate the nanodust from the purified water. If you fail to recover them, you've just introduced heavy metal nanoparticle pollution into the water supply.
Which completely defeats the purpose of an eco-friendly system.
Exactly. I mean, by immobilizing the catalyst inside a solid PMMA film, you eliminate the need for recovery centrifuges. You gain robust chemical resistance and mechanical integrity. Furthermore, you prevent the particles from aggregating or clumping together, which would reduce their surface area and kill their efficiency.
And the researchers backed this up with hard data, too. I was looking at the X-ray diffraction and scanning electron microscopy results.
Yeah, those imaging techniques proved the nanoparticles were perfectly and evenly dispersed throughout the polymer. They also showed that embedding the rust didn't alter the underlying chemical structure of the PMMA. The structural shield was completely intact.
But wait, if we've successfully wrapped our catalyst in this impenetrable, waterproof plastic shield, how does the contaminated water ever reach the rust? Haven't we just locked our microscopic incinerator inside a vault?
That is the fundamental paradox they had to solve. PMMA is highly rigid, and more importantly, it is naturally hydrophobic.
Right, it repels water.
It actively repels it. Because of this structural rigidity, it severely limits solvent penetration. The toxic dye molecules floating in the water can't physically reach the active iron oxide sites locked inside the plastic. If the pollutant can't touch the catalyst, no reaction happens.
So they had to find a way to open the vault doors without destroying the vault itself. The paper details a seemingly counterintuitive step where they intentionally damaged these pristine films.
What's fascinating here is the precise limitation of that damage. They subjected the cast films to a harsh surface treatment. They submerged them in a solution of hydrogen peroxide H2O2 for 24 hours. Following that chemical bath, they blasted each side of the film with pure UV radiation for an hour.
But wait, if we are breaking down the polymer chains with UV and peroxide, aren't we just degrading the very shield we built to protect our nanoparticles? How does the whole thing not just fall apart in the water?
It's a delicate balance. The hydrogen peroxide oxidizes the functional groups of the PMMA, specifically the carbonyl groups. Concurrently, the prolonged UV exposure causes photochemical chain scission. It literally severs the polymer chains on the surface and creates new, oxygen-containing functional groups.
So they are chemically fraying the edges of the plastic.
Only the superficial layers, though, up to about 100 microns deep. They verified through rigorous mechanical testing that this shallow surface treatment does not compromise the overall mechanical strength or reusability of the film, but it fundamentally alters the surface chemistry. It transforms the film from being highly hydrophobic to incredibly hydrophilic.
Meaning it suddenly loves water, it wants to absorb it.
Before this treatment, the most optimal film they cast had a water uptake of a measly 3%. It was a brick wall. After the hydrogen peroxide and UV treatment, that water uptake jumped to a massive 25%. They carved microscopic chemical pathways for the water and the dissolved dyes to rush into the matrix and interact directly with the embedded iron oxide.
Now that the floodgates are open, we can look at the actual performance data to see this microscopic battle play out. The researchers tested several different compositions, but the champion composite was designated HPF5.
Right. HPF5 featured an optimal loading of 3.32 weight% of the F2O3 nanoparticles within the PMMA. They submerged pieces of this specific film in a 5 milligram per liter solution of the toxic dyes and turned on the UV lights.
The contrast between the untreated locked vault and the treated open vault is staggering. The data shows that the untreated HPF5 film, after 60 minutes, only managed to degrade 51% of the crystal violet and about 62.3% of the rose bengal.
A sluggish performance caused by the inability of the dyes to penetrate the surface.
But the treated HPF5 film, in the exact same 60-minute window, degraded 93.5% of the crystal violet and 85% of the rose bengal.
They tracked the speed of the reaction, and it followed a Langmuir-Hinshelwood simulation.
Okay, let's translate that for the listener. What does a Langmuir-Hinshelwood simulation actually tell us about the chemistry happening in that beaker?
It is a mathematical model used to describe reaction kinetics on the surface of solid catalysts. It proved the reaction had a first-order correlation.
Meaning?
In plain English, the rate of destruction was directly proportional to the amount of dye present. As the chemical floodgates opened, the iron oxide didn't get overwhelmed by the influx of pollutants. It just worked harder and faster. The rate constant for crystal violet jumped from 0.0105 to 0.042. The surface treatment literally quadrupled the speed of destruction.
Here's where it gets really interesting. It's like the iron oxide is a martial arts master that can only fight one-on-one. By adding the UV and H2O2 treatment, we just opened all the doors to the dojo, allowing a flood of opponents, the dye molecules, to rush in and get systematically dismantled into harmless carbon dioxide. But how does that destruction actually happen?
It comes down to those highly reactive oxygen species we touched on earlier. When the UV light hits the iron oxide, the holes left behind in the valence band react with the water molecules and hydroxide ions that have now flooded into the plastic matrix. This specific reaction creates hydroxyl radicals.
Hydroxyl radicals. I've read those are some of the most ruthless oxidizing agents in nature.
They are entirely uncompromising. They are highly electrophilic, meaning they aggressively seek out electrons. They attack the electron-rich double bonds within the dye's molecular structure, which, incidentally, are the same bonds that give the dye its vibrant color.
Oh, that's wild. So it literally bleaches the color out as it destroys it.
Exactly. Meanwhile, the electrons that were catapulted up to the conduction band interact with the dissolved oxygen in the water to create superoxide radicals and eventually generate more hydrogen peroxide within the system.
So the dye molecules are caught in a crossfire between hydroxyl radicals and superoxide radicals.
It is a systematic demolition. These radicals rip the molecular bonds apart. They shatter the complex rings of the crystal violet and rose bengal molecules into smaller, unstable aliphatic acids. The radicals then attack those smaller acids, breaking them down further and further until the entire structure collapses into nothing but H2O and CO2. The threat is completely mineralized.
And crucially, the plastic film survives this demolition derby. Because it's a solid, flexible sheet, you literally just reach into the tank and pull it out when the water is clean. You don't need those expensive nanoparticle recovery centrifuges.
The researchers tested its durability rigorously to prove its viability as a replacement for current tech. They took the treated HPF5 film, washed it, and reused it for 6 consecutive cycles. Even after 6 full battles against these highly toxic dyes, the composite showed excellent stability with only a microscopic drop in efficiency. The structural integrity of the PMMA held up perfectly, preventing any nanoparticles from leaching out into the water.
That is the ultimate goal, a system that cleans the water and leaves absolutely zero secondary pollution behind. It's an incredible piece of materials science. But moving from a highly controlled laboratory beaker to real-world industrial application is always the hardest step.
Well, absolutely. The transition to large-scale municipal or industrial water treatment plants presents significant engineering challenges. This raises an important question. How do we design a water treatment plant where every drop of water passes precisely over an irradiated PMMA film?
Right, if you are managing millions of gallons of continuous wastewater runoff from a massive textile plant, you can't just drop a few strips of plastic into a vat. You would need miles of this film and a way to power it.
The chemistry is undeniably proven. The sol-gel synthesis works, the surface modification is highly effective, the mineralization is absolute. The next hurdle is logistics, specifically maximizing quantum efficiency. You have to ensure that your industrial UV light sources can penetrate deep into large turbid water tanks and strike the iron oxide embedded in the plastic evenly.
You'd probably have to design intricate baffles or spiral wound cartridges out of the film, maximizing the surface area exposed to both the water flow and the UV lamps.
And you have to scale up the manufacturing of the nanocomposites themselves into massive sheets. But the fundamental economic foundation is solid. PMMA, plastic, and iron rust are cheap, universally abundant materials. It's very promising for the future of water treatment.
So to bring this all together for the listener, we started with these terrifying toxic dyes that cause genetic mutations and severe eye damage, pollutants that stubbornly resist natural degradation.
Nasty stuff.
Really nasty. And by leveraging the specific band gap of lab-engineered rust, wrapping it in a transparent polymer, and using photochemical chain scission to let the water in, we created a self-contained demolition crew. Empowered by UV light and peroxide, it completely vaporizes the threat.
It shifts our entire paradigm of water treatment from simply trapping a problem to fundamentally erasing it.
And that's why you should care. Clean water isn't something we can take for granted. As industrial pollution grows increasingly complex, our solutions cannot just be bigger, finer sieves that pile up toxic sludge in a landfill. We need smarter, active materials. This research represents a massive leap toward truly circular, eco-friendly water systems where zero secondary pollution is left behind.
Systems where the water returned to the environment is as pure as nature intended.
Exactly. And it leaves you with a truly provocative thought to mull over. If material scientists can engineer a simple piece of plastic to harness sunlight and literally dismantle complex carcinogens into harmless water and air, what other invisible toxins in our daily environment could we destroy? Imagine just painting a similar nanocomposite onto our windows or coating the sides of our city buildings. We could turn the very architecture around us into a passive, light-powered air purifier. The solutions being engineered right now are becoming just as powerful and just as pervasive as the invisible threats.